So, let us talk about stability. Okay. Before formally defining stability, we will kind of do what we had done earlier. Let us say we have again xk plus 1 equal to the autonomous part is just xk plus 1 axk, okay. And then what we had said, let us start with some x naught. So, x1 is going to be a x naught, x2 is going to be a square x naught, a to the power n x naught. If we start with any arbitrary x naught and we want to reach origin, what is required is that all the eigenvalues of a should strictly lie between -1 and +1, okay. And what example that we had taken? We had taken the example of a scalar system right. If a is positive, then this will keep, the value will keep increasing, x value will keep increasing as n tends to infinity. If value of a is equal to 1, the value of x will not change, and if the value of a the real component of the magnitude of a, if it is less than 1, then it is going to be decreasing, okay. So, that is the concept, and that concept we can take it and apply it to the A matrix as well. And the reason why we can apply it to the A matrix is basically what we had considered earlier. So, let us do the Jordan decomposition. A is going to be V lambda V inverse, okay. This is a similarity transform. So, e to the power a is going to be V of this, and this we had seen, let us say if this is a diagonal form, this is nothing but e to the power lambda 1 t, e to the power lambda 2 t, and so on up to e to the power lambda n t. This is going to be stable only if lambda 1 is between -1 and +1, and lambda 2 is between -1 and +1, and lambda 3 is between -1 and +1, and so on up to lambda n, okay. There is a little bit of an issue over here, because lambdas need not only be real numbers, lambdas could be complex numbers. One thing that we did not cover when we talked about the Jordan decomposition is what is called a square decomposition. So, if an eigenvalue comes in complex conjugate pairs, then how do you do this decomposition? We had skipped that, if you recall our week 1 of module. So, let us not worry about that. If you just go look up any standard textbook, you can look up square decomposition, it is called, okay. I do not know if in lecture notes I have put square decomposition, no, I have not put that, yeah. But if you look up square decomposition, you'll actually realize how it works. So what square decomposition is let's say the value is a plus ib and a minus ib. The square decomposition will be a b minus b a. Okay, and the way the exponent in a case like that would work is that a square plus b square should be less than 1. Okay, so that's basically how it works, which essentially means that the modulus of your lambda should be less than 1, or your eigenvalues should lie in unit disk. Okay, so the term that you will hear for stability is a state space system a power n, sorry, yeah, you are right. This was based, yeah, thank you. It is not e power a. In fact, if we look at e power, a, then we should be looking at this in the left half plane. Thanks, sorry about that. Yeah. So, and again, if you have lambda to the power n, yeah, it's simply lambda 1 to the power n, lambda 2 to the power n, and so on up to lambda. Well, I should have used something else. Yeah. Okay. Thank you for pointing that mistake. Okay. Yeah. So yeah, this is the way the stability would work. Okay. So let's formally define stability, and there are two. Well, there is a third one also, but there are two types of stability. One is called Beaver stability, is called bounded input, bounded output stability. Okay. Asymptotic stability basically means that let us say you have your x, and at time 0 you start at some arbitrary point in your n dimensional space. I am just plotting one of those x's. Okay. Asymptotic stability means that eventually this x should come to the origin. Okay. So, this is what asymptotic stability means. What does Bibo stability mean? Bibo stability means that as long as your input is bounded, okay, your output also should be bounded. Okay. That is the statement of Bibo stability. So, asymptotic stability only looks at the autonomous part of your overall state space model, whereas Bibo stability looks at all the 3 matrices A, B and C. Okay. Bibo stability is for LTI systems is a much more stronger concept than asymptotic stability. Okay. What I mean by that is any system that is asymptotically stable will always be Bibo stable. Okay. But there can be a system that is asymptotically stable, but it may not be Bibo stable. The criterion for asymptotic stability, I will come to Bibo stability a little bit later. I will talk about another concept called controllability and then I will come back to Bibo stability. I mean, I do not need to do that, it is just would be easier to talk about Bibo stability then. Okay. The requirement for asymptotic stability is what I talked about earlier. Okay. You need to have your eigenvalues